this first project, we want to model the water level in a tank. As you can see in the clip, we have an inflow at the top and an outflow from a hole at the bottom. And clearly there is a link between inflow, outflow, and the water level H. For instance, if the inflow is larger than the outflow, the tank will fill up and vice versa. This could be considered as a very simple model of a stormwater attenuation tank used to mitigate the effect of heavier rainfalls and prevent floods. And our goal is to model the water level H as it evolves in time. So let's see the mathematics behind the problem. The outflow rate Q out is the product of the outflow velocity V out and the area A out. And we know that the higher the water level in the tank, the greater the velocity V out due to the pressure exerted by the fluid. This phenomenon is described by Torricelli's law that says that the outlet velocity depends on gravity and water level H. So now we have an expression for the outflow rate as a function of H. Given the initial water level H0, we have an equation that describes the evolution of the water level in time. And this equation says that the water content in the tank, which is the product of H times the area of the tank, AT, changes in time due to the net inflow, which is inflow minus outflow. And notice how the water level influences the outflow, Q out, which in turn influences the water level. So how can we solve it and find H in time? Sometimes we can find the exact solution to a differential equation, but often we solve them in an approximate way. So we will advance in time with small steps of length delta t and try to find approximate values of H. H1 after one time step, then H2, H3, Hn, Hn plus 1, and so on. So starting from our differential equation, the first thing we can do is replace this time derivative with this ratio, the water level change over a time step. And of course, this is not the exact derivative, but it is a good approximation if the time step delta t becomes smaller and smaller. So at a generic time Tn, this is our approximated equation. And notice that the simplest thing to do is evaluate the outflow rate Q out with the old value of the water level H, obtaining what is called an explicit method. Now we can divide by the area, multiply by delta t. And finally, we can bring all known quantities to the right-hand side, obtaining an expression for the new value of H. Now, if we know the previous value of the water level H, we can find the next. And we can see how it works computing a few steps. In the first time step, H0 is known, and by plugging in the data in the formula, we can find H1. And in the second step, H1 is known, and by using the formula, we can compute H2. But we need to repeat these steps so many times. And more precisely, they need to be repeated n times, where n is the number of time steps that we choose. And at each time step, we can compute the water level change in a time step based on inflow, outflow, time step, and area. Then we can add this delta to the old water level Hn, obtaining Hn plus 1. And we can also compute the corresponding time. And repeat these steps until the end of the simulation. So we will need a computer code to perform these steps automatically, and in the next videos we will learn how to write it.